Hey there, fellow science enthusiasts. Today, we're diving into a mind-boggling mystery that has physicists scratching their heads and questioning everything they thought they knew. It's a story of unexpected wobbles, theoretical clashes, and a quest for the truth that might just rewrite the rules of particle physics. So, buckle up and let's explore this fascinating journey together. Imagine a tiny, tiny particle, a muon, which is like a heavier version of an electron. Now, this muon has a unique behavior. It acts like a tiny bar magnet, and when you spin it in a magnetic field, it starts to wobble, creating its own little circles. The size of these wobbles is determined by something called the g-factor. If the muon were alone, its g-factor would be a simple 2, but the quantum world adds a twist. Every particle in the universe influences this g-factor, even the tiniest, most fleeting ones. So, when an experiment in 2001 showed that the muon's g-factor was larger than expected, it sent shockwaves through the physics community. For 25 years, this discrepancy has been a tantalizing hint of unknown particles, a potential key to unlocking the mysteries of dark matter. But in 2021, a new calculation seemed to put this puzzle to rest. The updated theoretical calculations matched the experimental results with incredible precision, to 1 part in 100 billion. However, this resolution created a new enigma. The older calculations, which were also based on experimental data, didn't match up with the new ones. So, what's going on? Are there hidden particles influencing the muon's behavior, or is something strange happening in the experiments themselves? One intriguing clue comes from a particle collider in Siberia. The VPP 2000 collider has been producing some unexpected results, with its experiments diverging dramatically from what other colliders have observed. This has sparked a flurry of activity among physicists, trying to decipher whether these conflicting measurements are due to different experimental procedures, or if new particles are indeed popping up. Now, let's talk about the muon's intricate dance. As it wobbles, it emits and reabsorbs particles like photons, which in turn release other particles, creating a complex chain reaction. Every particle in existence has some impact on this movement. So, when we measure the muon's g2, the excess wobble, we're essentially getting a glimpse into the quantum world, a window into the universe's particle population. In 2013, an upgraded experiment at Fermilab took even more precise measurements of the muon's g-factor. To prepare for this, physicists had to understand the muon's chains of emission and reabsorption in extreme detail. This is where things get tricky. The strong force, which binds quarks into composite particles like protons and neutrons, is notoriously difficult to deal with. Standard theoretical techniques don't cut it, so physicists had to get creative. One approach, called the data-driven method, involves measuring the behavior of quarks by colliding electrons and positrons. The more quarks appear in these collisions, the more they affect the muon. Using this method, physicists calculated the expected size of the muon's magnetic wobble, and the results sharply differed from Fermilab's measurement. But another theoretical calculation, using a technique called lattice QCD, told a different story. Lattice QCD is like a 3D grid that simulates the overall behavior of quarks. It's a bit like weather forecasting, where meteorologists divide the atmosphere into boxes to predict changes. This technique has been refined over a decade, and now, it seems to agree with Fermilab's results. Many physicists believe the muon mystery is solved. The extra wobble can be explained by known particles and forces. But why does the data-driven method indicate otherwise? To unravel this, physicists are digging into the electron-positron collisions. They're questioning what's really happening after these collisions, especially at the VPP 2000 collider in Siberia. When a new detector was installed in 2010, it produced surprising results, showing a significant change in the rate of pion production. This has led to a thorough scrutiny of the measurements, with no apparent issues found. But the discrepancies remain, leaving physicists with a choice. Either unknown particles are influencing the quarks, or there are overlooked details that make the quarks appear to misbehave. This mystery has physicists excited and confused in equal measure. It's a reminder that even with our advanced understanding of the universe, there's still so much we don't know. As one physicist put it, there are 4 decades of measurements that paint a completely different picture. There is so much still left to do.
So, what do you think?
Are we on the cusp of discovering new particles, or is there a simpler explanation waiting to be uncovered? Let's keep exploring and questioning, because that's the beauty of science. Until next time, keep wondering and keep learning.